Hey guys, it's Hal, and welcome back to ChamAcademy. So whereas we covered elastic and inelastic collisions in our previous videos, we're off to the topic of completely inelastic collisions. To understand this concept better, let's take a look at the example. During a spacewalk, three astronauts, wearing jetpacks, approach each other at equal speeds along equally spaced lines at an angle of 120 degrees. As the astronauts approach each other, they take each other's hands. If the astronauts come to rest after colliding, what conclusions can you draw? Okay, so let's start by drawing this out. We have three astronauts. First one we'll call Blossom. Second one, we'll make it Buttercup. Third one, which is blue, will be Bubbles. These astronauts are supposed to be colliding into each other. So, let's start by drawing their velocity vectors. And remember, the astronauts are 120 degrees apart. What we must take into consideration is the fact that they come to a complete stop. And since they come to a complete stop, we must assume that there is no velocity after the collision. This also means that the kinetic energy is lost. So what do we know for sure? Well, we know that the velocities and angles are the same. So how do we relate the two? Well, the laws of momentum state that momentum is conserved throughout every equation. So in this case, if astronauts come to a full rest, their final momentum is zero, which means the sum of their initial momenta should also be zero. So P of Blossom plus P of Buttercup plus P of Bubbles, and then Buttercup, sorry, mix up the colors, equals 0. And since the astronauts are equal angles apart and the sum of initial momentum is 0, and momentum is calculated using P equals mv, we can make a few assumptions. The first one, which is rather important, is that astronauts have the same mass. Why can we assume this? Well, it's because for the sum of the initial momenta with equal angles to equal 0, the astronauts, traveling at equal velocities, would have to have the same magnitude of momenta. Now, with this knowledge and using the momenta formula, equal momenta and equal velocities result in equal mass. Now, I know what you're thinking. How? What does it have to do with completely inelastic collisions? Well, remember that in all types of collisions, momentum is conserved. But what differentiates collisions is what happens to kinetic energy. In completely inelastic collisions, kinetic energy is lost and objects stick together after the collision. So in this case, the final kinetic energy is 0 and the astronauts stay together as they hold on to each other's hands. To prove
this is actually quite simple. We can just give the astronauts values to show that their momentum vectors equal 0. So for Blossom, let's just say she's going at 5 meters per second down. Let's also say she has a mass of 50 kilograms. Let's put that down, 50 kilograms. To get her momentum, we just multiply her speed by her mass. So 5 meters per second times 50. So Blossom has a momentum of 250 kilograms times meters per second. Let's put that down. For Buttercup and Blossom, though, they're coming at an angle, meaning they have an x and y in their momentums. With a horizontal, Blossom would be perpendicular with 90 degrees, meaning Buttercup would be 30 degrees away to add up to 120. To get her momentum in the y direction, we multiply her y speed, or sine 30 times 5 meters per second, by her mass. So let's put that down. P at y for Buttercup would equal sine 30 times 5 meters per second, which is the hypotenuse, using our trig knowledge, by her mass, which is 50. So Buttercup's momentum in the y is 125 kilograms times meters per second. And of course with sig figs, it becomes 130 kilograms times meters per second. Bubbles is coming at the same angle and speed as Buttercup, but in the opposite direction. So let's put Bubbles. Bubbles, let's just draw this out here. She's also coming in at 30 degrees. So their y momentums would still be the same. So P at y of Bubbles equals P at y of Buttercup. And of course, both these momentums are in the up direction. Now, in the x, Buttercup's momentum is the cos of the angle times the speed by the mass. So cos 30 times 5 meters per second times 50. So Buttercup's momentum in the x becomes 216.5 kilograms times meters per second right, or of course with sig figs, 220 kilograms times meters per second. Bubbles' momentum in the x, coming in the opposite direction, would be the same magnitude in the negative. So let's put that down. Bubbles' momentum in the x is equal to negative Buttercup's momentum in the x. Okay, so let's add up their momentums. In the y, Buttercup's momentum is 125 kilograms times meters per second, plus 125 for Bubbles, but for Blossom, it's plus negative 250 because she's going down. That will equal 0. In the x, Buttercup has a momentum of 260.5 kilograms times meters per second right, plus negative 216.5 because Bubbles is going left, plus 0 because Blossom doesn't have an x component, let's put that, plus Blossom is equal to 0, equal to 0. Look at that. Given equal speed, all the momentum vectors cancel out, only because the astronauts have the same mass. So in conclusion, we can say that the astronauts experienced a completely inelastic collision. They had the same momentum, and they had the same masses.